All right, welcome back. So today we are going to start our second portion of our solutions unit, and this is looking at properties of acids and bases. So a lot of this stuff is kind of a repeat of things that you would have had in previous science courses, specifically with a lot of these observable properties of acids and bases. So we'll just kind of hammer out some of these here. So what we have for acids, well, one way to test if you have an acid, you use litmus paper, and of course litmus paper turns red. Now for pH paper, so this is a paper that has multiple different things on it. You put a solution on it, and then you get multiple different color changes, and then you match them up with the color change on it. But what we'll get with pH paper is you match up the colors, and you get a pH less than 7. Now for acids, they are conductive, which means there are electrolytes. And another one, it's reaction with metals. So for acids, this is a very common thing, is they react to produce hydrogen gas. And of course, acids generally taste sour, and of course there is no characteristic feel. They basically feel like touching water. Now, of course, in saying that, caution, we never taste anything in a lab, and of course we never deliberately touch chemicals either. Now, as for our bases, so bases with litmus paper. Turn litmus paper blue. Same thing with pH paper, we're going to get a pH greater than 7 this time. They are conductive. But with our metals, there is no reaction with metals. And of course, last but not least, bases feel bitter, and of course they're slippery just like soap. So these are general characteristics that you should have kind of memorized a little bit, just difference between acids and bases, or how you can tell if you have one, like specifically the litmus test and this whole thing with pH. We're going to get into pH calculations later on in this unit, so that'll be next lesson. We're going to look at pH calculations. So this will be very handy to know. So pH less than 7, acid pH greater than 7, we have a base. If it's a pH at 7, it's neutral, so it's neither an acid nor a base. And of course, both are conductive, and only acids react with metals. All right. So that's just some of the characteristics. Now, what we are going to do here now as well is actually define what an acid and a base is and provide our first theory. So every unit has a major theory that permeates through it. We had our kinetic molecular theory for gases. We had our Lewis theory in our first unit, chemical bonding. And this isn't the first time you've seen this one, the Arrhenius theory. So we had Arrhenius theory on solutions, dissociation, and stuff like this. Now we have Arrhenius theory on acids and bases. So Arrhenius defined an acid is a substance that ionizes to form the hydrogen ion H+, AQ, in solution. So an acid is going to increase the concentration of hydrogen ion, and therefore it needs to contain the source of hydrogen. So for example, if we have perchloric acid, once again, this is a molecular compound because these are all nonmetals, but we will notice we do have that hydrogen ion there, so it is able to ionize to turn into H+, and our perchlorate ion. So that is how Arrhenius first described acids, is that they need to have that source of hydrogen, and of course they ionize. Now for bases are slightly different. So Arrhenius base is a substance that dissociates to produce hydroxide ions, OH-. So a base needs to increase the concentration of hydroxide, therefore it must contain hydroxide. So all the examples that we've seen that have hydroxide, so this is a polyatomic ion and it is negatively charged. So the only thing that can pair out with it is a metal ion. So that's why we have dissociation for the bases, but ionization for the acids. The acids are molecular, the bases are ionic. So for example, if we have something like lithium hydroxide, it will dissociate to produce the lithium ion and the hydroxide ion. Now, this theory does have some limitations, which we'll look at probably next week. It won't be, I don't think it's in this series of lessons for this week. It'll be next week. We'll look at the limitations, what happens. But just for right now, you are going to recognize an acid is going to have the hydrogen in it, so a source of hydrogen. So it's either hydrogen on the left, or remember you see the combination COOH, right? So this hydrogen is acidic in that one right there. But then again, that's something how you always recognize acids, because we dealt a lot with naming them and stuff like that. And then of course for our bases, you need to have hydroxide, so you need to see OH minus. If you do not see that, it won't be a base. Now, our next lesson is going to be calculations with pH and pOH, but we're just going to go through kind of the preliminary stuff right here before we actually get into the hard calculations for it. So for pH and pOH calculations, we'll deal with this whole pOH thing later. But first of all, just kind of look at pH, what that is and everything like that. So first of all is, why in an acid, where does this hydrogen ion come from? Well, we know water is polar and it ionizes to a very small degree. As if you did ever check with a conductivity meter pure water, it is slightly conductive. Now, water being a molecular compound, it shouldn't. So this is how we kind of know that this must happen to a very small degree. So, however, from experimental data collected, scientists have discovered that the hydrogen ion is electrostatically attracted to the water molecule to form a partial bond. So this isn't necessarily exactly true. We can simplify it like this, but in actuality what happens is that hydrogen is attracted to water and we form something called the hydronium ion, or a hydrated proton. So the hydronium ion is a hydrated proton, which is just H3O+. Now for our purposes, H plus AQ is going to equal the exact same thing as saying H3O+. So that just means these are interchangeable. But depending on how we represent it, it's basically your choice. But just so you know, two of these here will be the same. So now that we kind of know that the proton will be attracted to that polar water molecule, now we can represent the ionization of water as H2O liquid going into H3O+ and OH minus. So this is just a different way of representing the ionization of water. So that's what I have. So from here on, if you see the hydronium ion or the hydrogen ion, they mean the exact same thing. So this is what I have written up above. So that's just in case if you do get confused, or some of the equations that we see for pH, where you see either the hydrogen ion or the hydronium ion. So just be careful with that new term. They mean the exact same thing. Now, in pure water at SATP conditions, the hydronium ion concentration is very low because 2 water molecules in 1 billion will actually ionize. So what we have is the concentration of hydronium and hydroxide is the same thing in pure water because of this equation up here. And the concentration is 1 times 10 to the power -7 moles per liter. So we're dealing with a super small concentration here, so that's why pure water is only slightly conductive. Now, this whole idea of neutral, so if we know neutral water, the concentration is moles per liter, so that is something that we've just seen on the previous page, and there's something I mentioned earlier as well, that for anything neutral the pH is going to be 7. Now for acids, if we think back to our definition of Arrhenius acid, an acid is anything that is going to increase the concentration of the hydrogen ion or hydronium. So for an acid right now, we have another way to tell if something is an acid because if an acid is going to increase the concentration of hydronium, that means the concentration of hydronium for an acid is going to be greater than 1.0 times 10 to the negative 7 moles per liter. And also from our previous page, the pH is less than 7. All right, so these are two definitions of an acid. Same thing with a base. We can do the same thing. We're going to know the concentration of hydronium is going to be less than 1.0 times 10 to the negative 7 moles per liter, and the pH is greater than 7. So this is just a way that we can actually classify acids and bases as well, based on concentration of hydronium and, of course, our pH. So you will kind of need to know how to classify acids based on two of those things. Now, just kind of summarizing this up here. So the greater the concentration of hydronium, the more acidic the solution. In acidic solutions, the concentration of hydronium is greater than that of hydroxide. Now, if we lower the concentration of hydronium or increase the concentration of hydroxide, going to be more basic. And in basic solutions, the concentration of hydronium is less than that of hydroxide. And if hydronium is equal to hydroxide, then the solution is neutral. So all this right here is actually just a way to classify both acids and bases based on their concentration of hydronium or hydroxide. Now, this whole thing about the pH, I know you guys have used this before and you've seen it. Now we're actually going to look at what does it actually mean. So pH stands for power of hydrogen or power of hydronium, right? Little p stands for power, the H stands for hydrogen. Now, this was just developed as a way of communicating the hydronium ion concentration. That's it. Now, we use a logarithmic scale or a log scale. So if you haven't seen this in math yet, you will at some point, but on your calculators, you'll see a little button with the function log. So all of this is just a mathematical function. So you guys will see that if you haven't already. But this uses a log scale, basically used to narrow a wide range of concentrations into a scale between 0 and 14. So that's as wide as the pH scale goes. So basically we take concentrations that can range the gamut from 1.0 times 10 to the power negative 14 to 1 mole per liter. So we're looking at a lot of different things here, and it narrows it down. So the pH has no units. So this is one of the very few times that I won't worry about units for you guys if you're saying pH. And in general, the exponent number equals the pH value. So this is extremely simplified, but you should kind of see that. So what that means, if you have something like 1.0 times 10 to the power negative 7, and we've seen this, you could say that the pH should be close to 7. Now, this is going to hold true when the pH values are simple integers and the concentrations are simple powers of 10. So where 1 is a power, 1.0 times 10 to the power negative 7 is a power of 10, right? So we can use this idea as well. Now that means that we cannot say the exact same thing. So if we get 7.5 times 10 to the negative 2, we cannot say this is equal to a pH is equal to 2. We can't say that because this is not a simple integer, and it's also not a simple power of 10. So that's what that means. It's only if you get a 1.0 times 10 to the power of something that this whole idea will work. But when we get into the calculations for it, you don't need to worry about this whole note because you're going to calculate everything anyway. So for example, same thing is going before it. Now, if we have something like this, and we just kind of did this on the previous page, if we have 1 times 10 to the power negative 8, this is a simple integer, and it is to the power of a 10. So in this case right here, we have 10 to the power negative 8. The pH is going to equal 8, and we know it's basic. So if you think that you can get the other two, please pause the video and go for it. But if not, I'm just going to go through them here anyway. So this one here, you get 1 times 10 to the power negative 4. So because same thing, we're starting with a 1, there's no decimal, so it's a simple integer, and it is an exponent of, or a factor of 10 there, or a power of 10. We can say the pH is 4, and that means it's acidic. And just like this one right here, we have 1 times 10 to the power negative 7, so the pH is equal to 7, and it's neutral. Now the last thing we're going to cover for this particular lesson is just what the changes in pH means, and this is before we actually get into the calculation. That'll be next lesson. So last thing I'm just going to leave you with is the change of 1 pH unit is equivalent to a 10, that's 10, tenfold change in the hydronium ion concentration. So what this means by a tenfold is that however many pH units, we raise 10 to the power of, well, how many pH units this changed to. So I'll just kind of give you an example here. So where it says how much would the hydronium ion concentration change if there's a change in 10 pH units. So for a change in 3 pH units is a change in concentration by 10 to the 3, or this is 1,000, right? So this 3 value right here, change in 3 pH units, it goes right here. So that's what a tenfold change means. All right. Now with that, if you can follow that, and then of course think you can get the other two, please do. So example 2, pH of Coke is close to pH of 4, while pH of lemon is close to 1. How many times more acidic is the lemon than Coke? And an ammonia cleaning solution is has an approximate pH of 10, while a laboratory solution of sodium hydroxide has a pH of 14. How many times more basic is the sodium hydroxide solution? So if you think you can tackle these here on your own, please pause the video and please tackle them. If not, I'm going to put the answers up to these here in 3 seconds. And we have our answers right here. So to figure out how many times this more acidic is the lemon, we go pH of 4 minus 1, we get 3. So we take this 3 right here and we put it to the power, just like up here. So the lemon is 10 to the 3, or 1,000 times more acidic. And we follow the exact same thing for the ammonia example, where we go the 14 minus 10. So we get, there's a change in 4 pH units there. So we take this 4 and go 10 to the power 4. So we know the sodium hydroxide is 10 to the 4, or 10,000 times more basic, right? Because we're going up the pH scale. So that is it for this lesson. I know there's a few examples, I think, in your workbook that will deal with some of these here, so please give them a try. And then, of course, I'll see you guys for the next lesson, which is going to be actually calculating pH and pOH and how we can tie that into concentration of ions and a few things that we've done with the last unit. All right, see you guys for the next lesson.